Hello, Neural Network listeners. This is your host, Armand Priyadarshan. Today, we're joined by Dr. Santiago Segarra, a W.M. Rice Trustee Associate Professor in the Department of Electrical and Computer Engineering at Rice University. Dr. Segarra, would you like to introduce yourself?
Certainly. Hello, Armand. Yeah, first of all, thank you very much for inviting me to this conversation. It's a pleasure. I always enjoy talking about the work and the kind of things that I do. So I'm Santiago Segarra, as you mentioned. Um, I'm here at Rice. I've been at Rice since 2018. Before that, I spent 2 years at MIT doing a postdoc, and before that, I spent 5 years at UPenn doing my PhD. And even before that, I spent my first 23 years of life in Argentina. That's where I'm originally from. And broadly, my work lies at the interface of graph theory, signal processing, and machine learning. Essentially, how can we leverage the structure of graphs and networks to better learn from data defined on these?
Sounds good. So, what motivated you to pursue your current research interests?
Yeah. So I've been always very interested in interconnected systems. So the idea of relations between entities, it could be social networks, brains, biological networks, and so on. So I've been always interested in how the global structure and dynamics arises from local behaviors. That being said, kind of with that in mind, during my PhD, I started working on graphs from the beginning, slightly more from a theoretical computer science point of view, so some works on clustering. And then back then, this idea of signal processing on graphs started to emerge. So I started my PhD in 2011, so I had like 2013, kind of some of these ideas began to grow within the signal processing society. And these were very interesting to me. So at that point, they said, okay, this sounds like a good way to combine signal processing, which was kind of the society that I belonged to, with graphs that I was very interested in. Yeah, and that's kind of when I started work on this for 2014, 2015. And since then, signal processing turned also quite a bit into machine learning on graphs with different applications that we can talk more about this. But I think it was just kind of a perfect marriage between the idea of interconnectedness and graphs with data. And when this area started to arise, it was just very natural for me to get into it.
Yeah, for sure. It's like, as you mentioned, the interconnectedness of networks is really what makes them fascinating. Social networks are something that I find pretty cool. Like, I just watched like The Social Network a couple of days ago. I
Uh-huh.
really like that movie with like the founding of Facebook. And I do have like some experience with graphs. Like I've done like a little bit of work with like Tiger Graph and like NLP,
Uh-huh.
but I can't exactly say that I'm well versed in it. So can you give like a layman's overview of graph signal processing and what it is?
Yeah, absolutely. So the idea of so maybe you and some of the listeners might be more familiar with just classical signal processing in time, where you have maybe a signal that varies over time, and then for this signal, a lot of times we look at it in a Fourier analysis. So you look at slow and fast variations of these signals over time, and many times the fast variations, kind of the squiggly part of the curve, are associated with noise. So you can filter a signal in the Fourier domain. And then people were asking, okay, what if instead of having a signal defined on time, which is a very regular structure, what if we have a signal defined on a more irregular structure represented by a network? For example, a social network that you were bringing up. You might have data defined there, right? So this data could be what people like to do, or could be demographics, their age, their gender, maybe their nationality, kind of whatever data you have defined on this. This data can be noisy. So a question that arises, can you denoise this data just like you denoise a squiggly one-dimensional function, but now just data that lies in a graph? That's kind of a motivation to it. And the answer is yes. I mean, you can define the analogous of Fourier as a Fourier domain, but on the graphs. And once you have kind of the analogy of the time domain and the Fourier domain, but would be like the graph domain and the Fourier domain, then you can look at things like filtering or system identification, doing convolution, blind deconvolution, inverse problems, and so on. So kind of the whole machinery of signal processing in time just opens up for more irregular domains. The idea was to go and depart from just audio, images, or video, which are very classical and very well structured data domains, into more irregular domains. So now you might want to talk about not only social networks, but brain networks, biological networks, kind of you name it. All these things don't have the structure of a grid, but you still have data defined on these. So how can you process and learn from that? That's the essence of graph signal processing.
Will you really provide like an example of, for example, like noise within one of these networks and kind of like how denoising it would look like?
Yes. Yeah, right. So let's say that you are maybe, the signal that you have, you're just quantifying how much do you like a given product. So maybe you're trying to, you're interested in marketing or something, and then your signal is how much people would like a given product. So maybe you'll assess this from a questionnaire. Yeah, but this questionnaire, these are not perfect. Some of them might be noisy, might have missing data. Maybe some people you don't even have any data from. So just from partial information in your graph, you want to interpolate whether other people would like that product or not. But not only based on characteristics of those people in particular, but also who they are connected to. So in those cases, I mean, that might be more of an interpolation than a denoising problem, but still it's an inverse problem with data on a graph, and a very common one.
Thanks. That's a good clarification and kind of like shows like the power of graphs with, I guess, like completing that data and using someone's connections to kind of make inferences about them. It's
Mm-hmm.
cool.
Mm-hmm.
In your research, would you say there's like a project that you're the most proud of?
Well, that's a tough one. Uh, yeah, so there are kind of different features of projects that I like. So it's hard to just say one. And sometimes the reasons why one likes a project, if you're working on it, might be different than how the rest of the public kind of perceives it. So in terms of kind of math beauty, I would say that some of the work that I did back as a PhD student on metric projections of networks is maybe some of the things that I like the most. In those cases, we were just trying to derive an axiomatic framework on how to embed essentially a network into a metric space. That had some notions of category theory behind it. So it was kind of sophisticated and a lot of fun to work with. So that I liked a lot, more from the mathematical aspects of it. Of the stuff that I've done recently, to be honest, what I like the most is the versatility of the kind of tools and theory that we develop, which we can then apply in collaboration with domain experts from very broad fields. That's really excites me. So right now we have a lot of collaborations with people in communication, so working in wireless communications, so wireless networks, but also we have some collaborations with people working in metagenomics, in bioinformatics. So really it keeps you awake, because you just go from a meeting talking about new antennas and 5G and 6G, and then you go to the next meeting and then you just talk about genetics and metagenomics, and then maybe you go to the next meeting and now you talk about sociology and social networks, and and you go to the next one and you talk about urban infrastructure and resiliency of urban infrastructure. All these things are going on, and these tools are very horizontal to all these different verticals that I just mentioned. I would just say that is one of the things that I am most proud of, just the breadth of the kind of things that we're doing.
Oh yeah, that's awesome to hear about. It's cool to see how like the interdisciplinariness of your work is kind of being translated across these different fields. As like yeah, that's like cool to think about that you can like go through so many different subjects and still have that kind of connecting relevance with your work on graphs. and signal processing and network theory and all that. And do you have like an example of something that you applied to various different fields?
Well, yeah, I mean, yeah, so that's a good question, right? So there are some things that's relatively out of the box, but then those usually don't work exactly well, right? So now so graph neural networks, that's a big one. It's been big over the last 4 or 5 years. People have used GNNs, graph neural networks, to tackle many, many different problems on graphs. But many times these, again, don't work, or you don't get the most out of them by just applying them right out of the box, but rather you have to do it in collaboration and understanding, again, with domain experts. So just to give you two quick examples of what I mean by this. So in some of the work that we have in wireless communications, we wanted to do some power allocation, solve some power allocation problems. So given the channel state information, you want to allocate power to a bunch of transceivers. You could just replace this whole thing by a graph neural network. And we tried, and this gets you, so far. However, the best thing was to combine neural architecture based on graphs with a classical way of solving this problem. In that case, it was something called algorithm unfolding or algorithm unrolling. I mean, the details are not important, but the key thing is that people have been trying to solve these problems for decades. And they built a lot of knowledge and intuition of what things help in solving some of these problems. So instead of just trying to replace all that with just a neural network, you kind of try to complement, to kind of try to get the best of both worlds. So even though GNNs, graph neural networks, are indeed a common denominator across applications, once you get into a given application, it still has its own flavor. So GNNs, then we apply it, for example, to do repeat detection in metagenomic samples, which again, I don't need to get into the details, but just kind of trying to identify some important parts of genetic material. Again, in those cases, you can still do it as a node classification problem using GNNs, but in that case, we do a semi-supervised setup where first you get noisy labels from some existing domain-specific methods, which then you augment through learning with a GNN. Okay. So again, even though this is a common denominator across, the specific methods end up being quite a bit customized and more sophisticated than just an out-of-the-box implementation of a neural architecture.
Oh yeah, that makes sense. Like I'd assume that if you had like something that you had like a common denominator, you would like need a little bit of like specialization or a little bit of like fine tuning when applying it to something.
Mhm.
And on that topic, when it comes to like interdisciplinary collaborations, have there ever been like challenges that have arisen for you or like anything that worked really well? Do you have like any experiences that you'd like to talk about with that?
Yeah. So let's see. Let me think 1 second. Yeah. I mean, a lot of times introducing a collaboration could be high risk, high reward. So my main thing would be, if something is gonna fail, just to make it fail fast, I would say. So of the interdisciplinary projects that I have, if I worked on whatever, just 5 or 10 of these, then I started, 100 maybe or something, right? So, and by starting, I mean, I had an initial conversation with someone like, oh, it would be cool to apply these graphs to the design of material for this, and that. Okay, whatever, that's awesome, right? You have 1, 2 meetings, and then you have to assess very fast if this is going somewhere or not, right? So time is limited, energy is limited, so we need to allocate it to things that seem to have a more promising output. So what I would just say, and this is no one's fault, right? It's not my fault, it's not my collaborator's fault. It just either the problem was not a good fit or just this time of our lives wasn't a good fit, whatever it is, right? But my point would be, yeah, the first conversation, I would just have it with anyone on campus that wants to say, can we apply these graphs to studying the theory of music in the 16th century? Sure, let's grab a coffee and chat about it. But then if this thing is going nowhere, then that's it. Then we only invested half an hour on this and not half a year on this. So just fail fast and just keep the collaborations that look they're going somewhere.
Yeah, that's pretty funny, but it makes a lot of sense. If something's gonna fail, make it fail. But yeah, it's great. Uh, Moving on, you've done some work on authorship attribution using using network analysis. What are
Mhm.
some of the most like surprising findings from your research on Shakespearean plays?
Yeah, well, that would probably rank on top in the one of the interdisciplinary applications that I've done in my life. That one, it started more of as a pet project, trying to do some, as you mentioned, authorship attribution methods based on networks constructed from text. This was a long time ago, well before LLMs and so on. But then it was picked up. In this case, the collaboration was started from the other side. Kind of someone saw the paper that we published on the methodology, and this person, Gabriel Egan, he's a Shakespearean scholar, and said, "Hey, explain this to me a little bit more because I want to apply this to some of Shakespeare's text." So at that point, we started a very fruitful and fun collaboration with Gabriel. At that point, I was a student, so this was, of course, my PhD advisor, Alejandro Ribeiro, was also involved, and another friend of collaborator, Mark Eisen. And yeah, and then we applied this tool to a lot of Shakespearean plays. There were many subtleties that it had to be not the text that you would buy in the store, in the local bookstore. It has to be kind of the original text back from the 1600s, this and that. So Gabriel knew a lot about this. So we did apply it to this, and then without knowing it, we kind of found some interesting traces of the style of another contemporary author called Christopher Marlowe in 3 of Shakespeare's play, Henry VI, parts 1, 2, and 3. We actually had no idea what we were looking for. But then we showed this to Gabriel, and then Gabriel said, "Oh yeah, there's this kind of contention that some people claim that Christopher Marlowe actually collaborated with Shakespeare in writing these 3 plays, not based on the analysis that we were making, based on completely different sources of information, kind of where these people lived and when they talk and if they went to the same theater, whatever." So without really knowing it at first, we were kind of weighing in favor of some of the people within this controversy. And based on that work, again, as a cumulative source of evidence with others that would pile up, kind of that year, back in 2016, in the Oxford Shakespeare authorship dictionary or something like this, the Christopher Marlowe was actually officially credited as a co-author of William Shakespeare, of those 3 plays. So yeah, so kind of looking back and weighing in, again, it was not only based on us, but at least being one of the data points that would kind of change the authorship of a 400-old play, 3 400-old plays, was certainly a very funny and unexpected outcome of that original method for authorship attribution.
Yeah, we had to read like a lot of Shakespeare in high school, and there's like all these conspiracies and controversies about like first of all like his content, and then also like if he was actually the one writing his plays and like all that. So yeah,
Yes.
cool to hear
I
about
mean,
that.
that's how it started, to be honest. I mean, I could talk 2 hours about this, right? So of course we're not gonna do that, right? But that's a little bit how it started on our end. But then when we talked with Gabriel, like a Shakespearean scholar like Gabriel, he would just say that, actually this scholarly debate is not as much around, whether Shakespeare existed or not, or was another person and this or that. That is, more for like movies or these sort of things. But there is real scholarly debate about the level of collaboration that Shakespeare had or not with his contemporaries. So kind of that's where we ended up weighing in.
Yeah, and also I was kind of curious, how do you guys like determine the similarity in writing style between Marlowe and Shakespeare?
Yeah, well, for that, so again, as I was saying back then, so we generated things that we call word adjacency networks, so WANs, word adjacency networks, that capture. So in these networks, so the nodes are function words, so like prepositions, articles, essentially words that don't carry meaning by themselves, but just structure the way that you build sentences. And then these networks would just encode kind of how often you use these words and how often you use constructions of this word, kind of one word after another and so on. So this is just a quantitative measure of really how one constructs sentences, independent of the topic. And then we would build kind of some of these networks for the different candidate authors. And then we will build a network for the text to be attributed. And then we just compare them, just see some, computing some relative entropy, whatever between these things. We just compare them and then assign kind of the text to the author that is closest to it.
Yeah, I can like see that being like kind of relevant for like the rise of like language models as well. Because like, there's like a lot of like issues that have been coming up lately with like attribution and like kind of like seeing where like some piece of information was extracted from that database. So if there was like graphs within those language model databases and then like similarity functions that could kind of establish how similar that a generation is, something that's in the database, then that could also be like something that could be cool to